All right. Okay, I believe we're recording right now, and yeah.
Right,
Okay.
thank you, Pascal. Is this Pascal, by the way? Do you want to introduce yourself?
Yeah, sure. So I'll just firstly share the slides again in the Zoom meeting, and then yeah. So hi everyone. My name is Pascal. Yeah. Okay. Okay. Yeah. So as you can see up there, I'm a third year. And currently specializing in environmental biology, which has now been renamed to global environmental change. Yeah.
So he took this course before.
Yeah.
I think he took it.
As is she.
Yeah. So I'm a fourth year. I'm actually in the environmental geoscience program. I'm graduating this year. I've taken the course in person before COVID, during COVID, all that thing. And I've been doing this for 2 years. So I hope to hopefully help you guys for the midterms. And if you guys have any questions about geoscience, know that I will be trying to convince you to join the program. So if there's extensive manipulation going on, I apologize. I also brought cool rock samples, so hopefully we can get excited about that and make it a little bit more visual, because I know this is like an online class for you guys. So we'll get to mess around with that, as well as just review some concepts. This is not necessarily very thorough. It's not going to go into all the nitty-gritty details. It's just so that maybe you can make sense of those details, bring them all together, and get a storyline of what the topic is and what the lectures are about, right? Okay. So there are key concepts, 4 main modules that you guys are going to be tested on for the midterm, right? The first one was about just geoscience history, called the plate tectonic paradigm. How did we come up with this theory? Which, you know, it's a really cool theory about how, one of the theories about how Earth came to be, right? What are the scientists' approaches and all of that? The second module is actually what Earth is made out of. What are the composition, different layers, all of that. So maybe these are like keywords that are bringing up to mind. Then once you actually get to know about the Earth structure and a little bit more about what's it composed of, this is distracting you? You guys should, okay. Once we get to know a little bit more about the Earth structure, you guys covered how it moves, how all of the plate tectonics interact at all of these boundaries. And that kind of falls in. 3 and 4 are very similar. It's like 3 gives you the basis for understanding the dynamics, and then everything comes together in the 4th module, which is the Wilson cycle.
We have the slides.
Yes, so actually I will ask, are you guys all on the Discord server? No?
Oh,
How can we do this?
Is it the link to the Discord when I'm done?
So you guys have a link to the Zoom link, right? I think you all had it in the announcement. Maybe join there, and I think Pascal
yeah.
shared a
I'll
link.
I'll share it again.
So I think that's the best.
You're all going to be just joining.
Yeah, I think that's the best way to go about it. So if you want the slides, just go into the Zoom link. You might want to mute your camera because it might do like an echo effect. Yeah. Should I wait for you guys to log in before we start with the slides? Okay. We got time. This is not
Yeah,
gonna be...
we have plenty of.
Again, if you want to interrupt us, we're not TAs, we're not professors.
We are not.
Go for it.
Yep. I cannot. Oh boy, cannot see the link. Neither on desk. Okay, yeah, just hold on. We're gonna. Okay, I will share. Well, firstly, I'll share the link again. Okay.
You guys get it? No?
Almost in. We're getting more people in.
You have to like individually admit people to the room, so
Yeah, well, or as people come in. All right, let's try this again. Okay, all right. I just shared it again, and oh, why did I wrong? Okay. I know why everyone cannot see it. Okay, let's do this again. All right, there we go.
Yeah.
Okay, yep. I was sharing to the waiting room participants. Whoops.
All
right. Yes, welcome. Yes, just to answer, I guess everyone's
Okay.
Yep.
Are we good to go?
Yeah, so recording there is a recording going on. It will be shared as well as slides, and yeah. Okay, so let us proceed.
And also, if you guys are intimidated by the recording, we don't see you, we don't know who's talking, so don't worry about like asking questions.
Yeah.
Yeah, that's totally like it's on your discretion.
Yep. Okay.
So a little about the paradigms for those who just joined. These are the 4 modules that you guys are going to be tested on and covering. So the first module, which is a little bit about the history about geoscience. How did we come up with the plate tectonic paradigm, right? We came up with thinking that Earth was a plate, it was flat, and now we're thinking of it as a dynamic orange peeled process, right? So the first interest in geoscience, how did people actually become interested in learning about geoscience? And why did we start thinking about just Earth as a whole, right? So to be able to actually study geoscience, we needed maps, okay? And the first map that was actually ever invented was in the 1600s, and that was done by Francis Bacon. And it was a rough map, right? We didn't have all the GIS satellite remote systems that we have today, but it was enough to understand a little bit about the global view of how we thought Earth's continents and outlines looked like. And once scientists saw that with the curious minds, obviously they started asking questions, okay? And certain of the things they noticed is that later on, so this is like almost 2 centuries of looking at atlases and maps, right? After 2 centuries, about 1858, what they started to notice was that actually some of the continents' outlines could actually fit together like little puzzle pieces, right? If you look at the atlases, even back then, if you look at it, you know, North America, South America is very inaccurate, right? They didn't explore everything, but it was enough to realize how North America, South America, and Africa were like fitting jigsaw pieces, right? So how is that possible? Obviously, it has to be from something, from somewhere. So there are 2 possible views on how continents could have been once together and kind of split apart. And mind you, this isn't like the 19th century, right? The first view was permanentism, and that was view that the continents don't move individually, but Earth was kind of like a balloon, right? If you blow into it, okay, if you blow into a balloon, all of the letters, if you have a decorated balloon, they kind of expand or shrink depending on how old the balloon is. And they thought Earth worked the exact same way. So as time went on, Earth would cool, shrink, and because of that, Earth continents would kind of move as long as, you know, letters would move on a balloon, or as just contraction of the Earth themselves. Okay, so continents didn't move in the idea of permanentism, which is where the word comes from. It's permanently in place, but Earth as a whole would change its size or volume. The second view, or the second kind of class of theory of why people thought these were jigsaw puzzles and how the continents could have been once together and then separated, was mobilism, okay? And mobilism actually suggested, yeah, continents themselves move, okay? They move within the oceans. It's not just the Earth contracting and shrinking. But then became the big question of, okay, if continents were to move, what's driving them to move? You know, mind you, this is back in the 19th century. Science is very early, right? So there had to be then started this whole view of how is it possible? What's driving the continents to move? Okay. And Frank Bursley, so this is a little bit towards the beginning of the 20th century, suggested that continents actually moved because of the forces of the ocean. That was a lot of scientists believed in that. If you guys remember Alfred Wegener, actually, he also believed, he formed his theory in the early 20th century, died, but without seeing his theory actually come to flourish. But he also thought that continents could possibly move because of the forces of tides. But that was the big ick in his theory, okay? People, mind you, okay, here's the big thing. People always recognized and tried to understand that while everybody was switching to mobilism, they wanted to figure out how continents moved. So Alfred Wegener wasn't the first one that figured out continents drifted, because he wasn't born when mobilism even started. But what he tried to do is actually provide additional evidence on, okay, this is scientific proof, not just the jigsaw puzzles, but these are proofs that the continents were actually once connected. The way he did that, you can actually see it here, to the top left, right? Oh, actually I have a little thing here. Okay, so this is Alfred Wegener's work. And he actually suggested yeah, continents were once together. Look at this, the fossils match. If I put all of the jigsaw pieces together, glacier rocks, okay, when glaciers existed and they start retreating, they actually leave scour marks. And if he put all the continents together, he realized the scour marks matched, suggesting that these were the same glaciers that melted at the same moment and left kind of similar scour marks. So he used fossils, glaciers, and he also used different types of, what was it? What was the third thing that he?
Oh,
Does
what do
anybody
you say?
remember?
You say fossils, glaciers, and
Plants, thank you.
yes.
And he suggested looking at the plants, good job. That continents, if you look at South Africa, right? Or you look at South Africa and South America, the plants were very similar. Again, fossils, but more or less animal, but plant-like, suggesting similar climates, right? How do you get similar climates when now continents are like across the world from each other and have very different climates? So through all of this, Alfred Wegener just provided more evidence for mobilism and continental drift, but no one believed him. And the reason no one believed him is that he didn't provide the reason and a reasoning behind why continents would drift. He only provided evidence that continents were once together, but that wasn't enough for people to change their entire view on how Earth formed. Okay, you need evidence as a scientist. So all of his theories, basically, he was born in his continental drift theory or evidence was born in the early 1900s, and he was only recognized in the 1960s once he was long dead. Okay, Port Morton, as we say. And that's very unfortunate considering now he gets so much recognition, right? Now, one of the key features or key people that actually started proving or finding key ways in which the continents would drift is Arthur Holmes. So he actually was Arthur Holmes and Harold Hess, okay, which we're going to see. These were two scientists that actually worked in ocean basins, and they are actually, Arthur Holmes worked for the Marine, and he realized that in the center of those oceans, there are big ridges, like huge canyons. And although back then you couldn't really map the ocean floor that much, he thought of what we call the convection model or the seafloor spreading model, where actually what would be driving the move of the continents would be the seafloor actually being like a conveyor belt, or you know those belts when you're trying to go to the airport and you go fast, you're like a Super Mario Kart star, and you go faster. Yeah, so that same process at the middle of the oceans, they would actually spread and kind of rotate, giving enough force to push all of these continents apart. But once again, how? Why? Okay, scientists are always asking how, why. He only suggested that possibly the ocean currents could be, the ocean floors could be moving, and he proved that through paleomagnetism, which is what we see here. Okay, Harold Hess worked on it as well, and he looked, we're going to go through that. So he proved again, evidence for seafloor moving, but why is it moving? Big question mark. Okay. Another evidence that would possibly suggest that indeed the ocean floor was moving was discovered by Hugo Benioff, and he discovered that earthquakes, if he plotted the epicenters, which is where the rocks broke in the first place, creating that shaking, and he plotted all of these epicenters along the coastlines, which is usually where you see the most earthquakes, they formed a perfect parallel plane, possibly suggesting that it's actually the seafloor diving into the crust, right? So that provided, again, more evidence towards seafloor spreading, but how, why did it exactly move? And the whole thing was because of mantle convection, right? So it's only Harold Hess, which is in the late 60s again, and with Tuzel Wilson's hotspot tracks, that they actually tried figuring out that it was hot convection from the mantle and hot magma rising up at oceans, mid-ocean ridges, that then actually drives through ridge push, that drives this conveyor belt motion of the sea floor. And then they also then shrink and get colder towards the end of the lives, towards the end of the oceans, and then they sink, right? Because colder is denser in general. So basically it's a thermal convection model within the mantle, okay? And then Tuzel Wilson, which actually we're very proud to be a U of T alumni. I don't know if you guys knew that. He was a geophysicist downtown. He further kind of like put everything together, and he explained why oceans closed and opened based on all of the other scientists' work. So now everything kind of came together, right? From our first and early 1600s, kind of looking at maps and seeing that they match together, to providing proof that indeed the continents were actually together, to actually figuring out how they moved. That's how the plate tectonic realm actually developed. Okay, so by the late 1960s, we formed our plate tectonic theory. Okay, so it's a very relatively new science if you think about it. Reasons more to join it, a lot to discover. I told you I would do this. Okay, so we mentioned things like convection, mantle. You probably know this. This is a review slide. But let's go into Earth's structure. Okay. So Earth can actually be divided, if I look into here, Earth can be divided into about 5 layers. Okay. Some discuss 4 if you put the cores together, but in general, you have like a crust, right? It's crispy, it's cold, it's what we live in. It can range all the way from 7 kilometers to 70 to 100 kilometers thick, okay? Depending if you're oceanic or continental, we'll go into that. Then 2/3 of the Earth is actually mantle, okay? So the bulk, this is actually not to scale if you think about it, because 2/3 of the volume is actually this red thing, which is the mantle. It's ductile. Ductile meaning it's not a liquid, it's not a solid, it's malleable. It just moves. It's like very chewing gummy type of viscosity. And then in the center, you have an outer core. The outer core is actually liquid. Okay, we'll go into all of these details. And the inner core, which is solid. So I actually had a friend 10 minutes ago who showed me a meteorite. Okay, and that got me thinking. And meteorites are actually cores of other planets. So we never are able to actually go and detect the middle of the center of the Earth. The only access we have to its composition is through meteorites. So fun fact for you guys, I don't know if they mentioned that. So it's high in nickel. So a little bit about each layer, right? The crust, there's 2 types, oceanic crust and continental crust. Now here are 2 words, mafic and felsic, okay? So can anybody tell me what are some of the characteristics of oceanic crust that might differ from continental crust? How are they different? Denser, which one's denser? Yeah, okay, denser, good one. I was checking it on the slide, but it's denser, that's good. Now it says on there it's mafic as well, right? Does anybody know what mafic means? Yeah, so it's the composition, the chemical composition of the rock. So mafic rocks are generally dark, okay? So I forgot to bring a mafic rock.
Oof.
Bravo me. But I do have a felsic rock though, which is a continental rock, okay? So this is a generic, anybody name this? It's always on in your kitchen. Granite, exactly. Okay, this is pink granite, okay? This is usually a lot, bulk of the continental crust is actually this type of rock, okay? And it's specifically intrusive, we're gonna get into that. But felsic is usually white, grayish, pink, light colors, okay? That's the felsic compositions, and that's what most of the continental rocks are made out of, okay? Now, oceanic rocks, as you mentioned, are generally darker, okay? They're quite the opposite. They're darker, they tend to be a lot denser, and they tend to sometimes even be green, okay? So these are all characteristics, you guys can touch that later on, of difference between oceanic and continental. Now, also ways we figure out the composition, the thickness of the crust and things like that is through geophysics, okay? So this is a lot of words. Let me highlight some of the things we're looking at, right? So how do we investigate the layers of the Earth? It's through what we call rayology. I don't know if it's there. No, it's not. Okay, so add this to your slide. Okay, so the way we study the Earth or the different layers of the Earth, and we actually come up with this guy, is through rayology, which is just throwing seismic waves and seeing how they refract back. And through geophysics, we can actually identify the speed at which all of these seismic waves travel through different material. And that tells us a lot about the density, the hardness, and the heat of those materials. Okay. We do a lot of cool work at UTSC actually modeling those. So let me just leave it. There we go. Okay. So another thing about, and we'll go through that. I hope you covered this. Okay. The lithosphere. Okay. So the lithosphere is actually something that wasn't shown within this model, but it's actually a combination of crust and mantle. Okay. The lithospheres, think of this. Okay, you have all those plate tectonics. Now we know plate tectonics is driven by, as we said, large convection cells, and you have at the top here your plate boundaries. Let's say your oceanic plate. It grows here, okay, spreads, and then it dies off, okay, and then it's all lava, lava, lava. It gets so warm that it rises, and then it spreads, and then it cools and it goes down. That's convection model, right? So what's actually moving, okay? What is this? It's not just crust, okay? It's actually lithospheric plates, okay? And lithospheric plates is equal to crust, okay, which can be oceanic or continental, plus the upper mantle. So the mantle, which we said was 2/3 of the volume of the Earth, isn't actually consistent in its characteristics throughout the whole depth. Okay, it's about 2,000 kilometers or 2,000 man, I don't know how thick it is. I forgot this. How thick it is? How thick is the average thickness of the mantle?
Oh, crap, I forgot.
I don't think it's important, you guys.
Yeah, I
but
don't think
okay.
it's too important.
Yeah, so throughout its whole thickness of the mantle, it's not uniform. It makes sense, right? A lot of it is actually heated through radiative heating from the core, okay? And that heat, we're going to go into it. It comes from isotopic decay, things like that. Anyway, so that heating from the core, obviously, if you're going to go further away from the core, you're not going to receive the same amount of heating, despite the convection, right? So the top part of the mantle, which we call the asthenosphere, okay, is still malleable, but it's much harder, okay, than the below mantle, okay? It tends to be a little bit less rigider, okay? Less, what do you say? Less ductile than the below mantle, okay? So you can divide the mantle into upper and lower mantle, the upper mantle being the asthenosphere, and those two is what makes up the lithosphere, okay? And the average thickness of the lithosphere in total, so crust plus upper mantle, tends to be like about maybe 100 to 150 kilometers thick, okay? And these are what the lithospheric plates move. These are like when you think about the plate tectonic paradigm as an orange with different peels. I think they talked about this, right? Like you peel an orange and then all of these layers move. Those orange peels are a lithosphere, they're not crust. A lot of people get that wrong, okay? And so they float on top of the mantle asthenosphere. So the asthenosphere is below the lithosphere. So the upper mantle is not the asthenosphere. I did this like 3 years ago. God damn it. Asthenosphere is what's below the lithosphere plate. Okay, it's not the upper mantle. Go for it.
I understand it correctly. So the sphere would not be exposed. We wouldn't see it. We would see the crust, but not.
Yes, you can't access the mantle at all, right? So the only exposure you have to the composition of the mantle is when sometimes there's diamond mines, things like that, or diamond, what we call kimberlite pipes. They form naturally and they go really deep. Or when you have naturally so high flowing magma and high warm that it even skips the whole process of staying in the mantle, it goes straight to the earth. But it's much, much, much deeper than anybody can go into.
That is what
It's the crust plus the upper mantle. They're both staying in contact and moving together. And those are floating above asthenosphere, which is the lower mantle. Does that make sense? I might have confused everybody by just saying the asthenosphere thing. I apologize for that. Okay, so you have, this is important, that's why. Okay, you have your crust, okay, oceanic or continental, plus upper mantle, okay, which is like generally it's colder, okay, than the general rest of the mantle because it's further from radiation. That is your lithosphere, Okay, and this moves through plate tectonics over the asthenosphere. And the asthenosphere, okay, is actually it's softer and it tends to be very ductile. So that's why this rigid lithosphere, it's harder than the underlying asthenosphere. So it kind of just like floats, like let's say a boat on water, right? Why doesn't water go along the boat? It's because it's much less dense and less rigid than all of the boat itself. That makes sense, right? Everything is connected together, but the asthenosphere, it's not connected to anything. So it's just, it allows it to move about. Okay, does that make sense? Okay, good. Now, okay, so these again, lithosphere about 100 to about 150 kilometers thick. Now, the mantle, which is the asthenosphere and anything below it, right, is made up of very ultramafic, what we call, which is ferromagnesian. It's synonymous, okay? Very ferromagnesic silicate minerals. That meaning, I don't know if you guys heard of olivine, the green mineral, yeah? Okay, so usually if you look into the mantle, it's not red, okay? A lot of people would think, oh, I heat up to such high degrees, probably everything's red and looks like I'm, blowing glass, right? No, it's actually green. A lot of it is green because that mineral is stable at those high conditions. And those very high in iron and magnesium content minerals and rocks are what we call ultramafic rocks, okay? Here. They're rich in magnesium, iron, and mafic, okay? So they would be very dark or generally very green, okay? And if you put these minerals to the surface, they're not stable. They like to be in high pressure. That's why we don't see it a lot, and we don't see green rocks here. Okay. Again, it makes about 2/3 of the Earth's mass and about 85% of the Earth's volume. And that's what the lithospheric plates are moving over. And that's what we're seeing here, okay? So mantle convection, we did go over this, right? Warm rises, cold sinks. Think about this. Why do, the reason why when you boil water to put your pasta in or rice in or whatever, the reason why there's actually bubbles is because the warm water at the bottom of that pot is so warm that it moves with a lot of speed. Once it reaches the surface, it moves, kind of displaces the water that was already at the surface. So it kind of creates a boop, too much water at one place, and that's why it bubbles. Okay, if it wasn't gas, it's not like a carbonated drink, right? The reason why is it's actually the result of mantle convection or convection in general. Questions about that? Nope. Okay. And so the convection, mantle convection, it says mantle, right? But convection happens in the mantle and the lithospheric plate move because of mantle convection, okay? Don't say that convection happens in the lithosphere. It's not true. It happens in the mantle. And the lithospheric plates are just moving because of it, okay? Now the core, there's actually two. There's the outer core and the inner core. It's composed of high iron and nickel, okay? It's about 33% of the Earth's mass. So that kind of shows, right? If you have 2/3 of the Earth's mass is the mantle, and then 1/3 is the core, then what's left for the crust? Barely nothing. Crust is very, very thin compared to the rest of the Earth. Okay, it's like 0.000. So the inner core, whether it's the inner or the outer, they have very similar composition. Just think nickel, iron. Okay, again, same compositions you would find in meteorites. The only difference between the outer core and the inner core is that the outer core is liquid and the inner core is solid. How do we know this? Using seismology or rheology, okay? So when you throw out seismic waves, okay, down from, let's say, an area, geophysics would study this, you can determine how fast by looking at how fast it reflected, your seismic waves reflected. So generally when it's a uniform, it's indicating the same layer, okay? And then at those boundaries, don't think of it as like a filter between these two layers, right? What changes is just like light refraction, right? Remember Snell's law of refraction, all the trauma from physics? Yeah, okay. So if you actually apply this, remember when we went from like one material to the other, it got refracted. This was for like an electromagnetic wave, right? And you have this thing, same thing for mechanical waves and different types of material, like where it's traveling. Okay, works the same way, refraction. So if you can calculate this angle, you can actually calculate, okay, there's a change in the material. And what they realized is that mechanical waves, some mechanical waves don't travel through liquid, right? Because they need solid to actually propagate. And so when they realized that the waves wouldn't travel through the outer core and there would be created a shadow zone, okay? Because waves would actually go here, they would hit the outer core, so the outer core, and instead of being refracted and then coming through, they just were completely reflected. They wouldn't go through this area. So they would move along, but there created some areas around the Earth where you just wouldn't receive any seismic waves. Why? Because of this liquid outer core. So that's how they figured it out. They figured out these waves. Okay. So there are two types of waves that actually can be created transmitted within the Earth. And this is valid for earthquakes as well. Okay. Whenever you're creating a little bit of movement within the Earth, you have primary waves and secondary waves. Okay. So primary waves, think of it as, what's the name for it? The dog in Toy Story.
Stinky.
Yes, a thingy, this thing. The metal spring. There we go, spring. So the way if you compress the spring in one area, right, and you release it, that compression would then propagate to the rest of the spring until reaching the end, right? So this is initially, and then that compression will move here, and this will go back to its normal state, right? If you think about it. So this is P compressional waves, okay? So that's how compressional waves are translated or how they move. Secondary waves, they're your typical, okay, you have a massive rock, it moves side to side, up and down, that type of wavy motion, okay? So compressional waves can actually happen in solid and in liquids, okay? Because you just need an extra amount of pressure somewhere, and that can happen in any type of material, even liquids. Secondary waves in water, it doesn't really transmit that much. It's going to dissipate really fast, or in any type of liquid. So these are the secondary waves, didn't transmit through the outer core, and they allowed us to identify that the outer core was liquid. Okay, not the primary waves. Does that make sense? Because the primary waves would actually go through, get refracted, but they would actually go through and they wouldn't create a shadow zone. Make sense? Okay. So remember this is really important to know. Difference between primary waves and secondary waves. They can be emitted through geophysics or even earthquakes. Okay, two types of waves. Generally, primary waves are also much faster. So if you were, let's say, an earthquake happened here, okay, and you were a little station right here, a geologist waiting to get data to do his PhD, you would probably get, this would be your record, you would get an increase in motion detected earlier on. Those would be your P waves. You would wait a little bit, secondary waves, and then you would get your surface waves, whatever, which is actually what's felt by people, okay? So always primary waves are faster, so they're detected first in an earthquake. And that's all you guys really need to know for the first two modules. Okay, now we combine the third and fourth modules together. And then that's the plate tectonic movements, how they move, and also how they develop the Wilson cycle. Any questions before we move? I know we've been talking pretty fast. No? Do we need a break? No? Okay. Let me know if I'm talking too fast or you guys.
Wait, seismology and the rheology are the same?
Also, one thing that the diagram that you draw for the Snell's law, that was probably wrong because the angle of, yeah.
I know. Usually you would go from, yeah. Thank you. You were not going to be tested on the Snell's law. Okay, so how do the lithospheric plates actually move? Okay, so there's three types of boundaries because we said they were separate, right? They moved individually and that depended on the convection. So when two plate boundaries actually connect or touch each other, there are three ways they can actually interact. So it can be convergent boundaries where two plates are actually going towards each other. There's divergent boundaries where they actually where the plates actually go away from each other. Can you guys guess where this happens? From our models and what we've been talking to? Where do we see like two plates moving away from each other? Subduction. Subduction. Subduction is our Wadati-Benioff zones, where you have a subduction plate over.
When subduction, or like when a subduction happening on both sides, they move away from each other.
So that would be the
Mhm.
ocean floor,
Yeah.
sea, ocean floor, mid-ocean ridges,
Mhm.
right? Yeah. So those are the divergent boundaries. Subduction zones are actually the convergent boundaries
Mhm.
because they come together. But I see where you were going with it though. Okay, so probably in the middle of the oceans, you would see that separating, okay? And then transform boundaries is actually California as an example, or Turkey recently, right? Is actually when two plates tend to move side by side. Okay, so none of it is going up, they're not going up towards each other, none of it is sinking, there's no mountain formations, it's just side by side. Okay. Now, let's look at the dynamics. Did you add this?
Oh, yes, don't worry.
Okay, convergent boundaries, right? When they're coming together. So I know it's a lot of classification. You have three overarching ways they can come together. Now, if they come together head on, okay, there's three types of ways they can interact based on who's interacting, okay? If you have an ocean plate, okay, versus a continental plate, okay, green is going to be my continental, this is going to be my ocean, okay? We have continental plates are lighter, less dense than oceanic plates, okay? So what happens is that actually the denser, heavier ocean plates tend to go below. They overcome that interaction and they tend to fall below the continental plate, okay? And then the continental plate will always go above an oceanic plate if they come together, okay? So that's our first, our second type of interaction, okay? Between those two, interaction of convergent margin is ocean continent convergence. So does this ring a bell? Does this look like anything we've been talking about? Exactly, subduction zones, okay? So these are called subduction zones. Okay. And these are actually very, very dangerous, okay? The reason why is that when they go down, okay, when the oceanic plate goes subducts, they reach higher temperatures and they tend to melt. What happens when you have rocks melting? They move down. Why do they move up? Do they become
Let's get.
through, are they still rocks? Magma. Magma.
It comes out as lava.
Exactly. Okay, magma is under the surface, lava is at the top of the surface. Exactly. So in the subduction zones, you tend to have the oceanic, the ocean little crust or the oceanic lithosphere going under the continental lithosphere, and then magma forms. Okay. This magma can then stay here, okay, and become what we call plutonic or intrusive rocks. If they stay magma, condense into rocks and never go to the surface, or they can erupt. We can have a little volcano. Too bad for the people living there. Becomes lava, and these cool so fast, we call them extrusive or phaneritic rocks. I should probably write this somewhere else. Except if we have it written down somewhere. No, we don't.
So,
Okay. So let's call it here. Extrusive here, volcano rocks are phaneritic, volcanic, or extrusive. These are all the same ways to describe these rocks. Why are they different? They cooled really fast, okay? Because they became lava, they got erupted at the surface. If the magma produced stays underground and cools, because it went a little bit up and not enough, or it doesn't have enough power to actually go into the volcano, they become plutonic, intrusive. Actually, this is the opposite word. There you go. Plutonic, intrusive, or yeah, rocks. Okay. To make it a little bit more interactive, I actually have two rocks here that are probably of the same composition. Okay. We talk composition can be felsic, mafic, or sometimes intermediate. Okay. So in between the two. Same composition, about the same color. Okay. Same types of minerals. Guess which one got erupted? And cooled at the surface? Left hand? How many people vote this hand? Okay, how many people vote this hand? Okay. Cooled at the surface means they cooled really fast. That means the crystals or the minerals that were in the magma or the lava now didn't have time to grow as much. So they're very small. Now that I said that, which one? Everybody thinks this one? Yes. So this is actually an intrusive rock, an extrusive rock, okay? It probably formed from lava being at the surface. This guy probably formed through a lot of years of cooling, and look at how big the crystals are. Okay, we can even call this a pegmatite. So same composition, it's just that this one got sorted and actually formed crystals. This one didn't have time, cooled within a few seconds. In extreme cases, to show this even further, if it cools super, super, super fast, and let's say the bottom of the ocean, where it's probably like 1 degree, 0 degrees, okay? So it went from like -500 degrees to 0 degrees in less than a millisecond. You can actually have natural glass form. This is what we call obsidian, okay? So you guys can pass it around. But this is like the extreme case where it didn't have enough time to even show visual crystals, but it looks like glass, right? And then we also have, so this is in the case probably in like a very cold, maybe oceanic environment. And now, this is okay. And these type of rocks, again, extrusive, we're going through the extrusive rocks here. Yeah, rivers don't even. These extrusive rocks are probably same. They're erupted as lava, but more. This is, I think we covered it in the field trip. Okay, this is not on the slide, so I want to make sure we cover this. So in the field trip, do you guys remember something as such very high volcanic eruptions, and they cause what we call lahars and pyroclastic flows. Yes. Okay. So these are high temperature dust and lava that fall to the side of a volcano because of such a very brutal eruption. Okay. And what happens is actually rocks can form from this, but those rocks, again, you can't see crystals, but they tend to actually trap air bubbles. Okay, because they're so gaseous, when they actually form, it's vesicular, VESICULAR. So that means that they actually trap and you can see the air bubbles. So, oh, we didn't accept that. Don't say anything. And you can pass it around.
Use both hands.
Anyway, so it's an example of why, right, that the fact that it trapped all those air bubbles, it makes it very, as you'll see, I can't say it. So it's pretty surprising, right? So these are things where the time and the type of eruption really depends. Looking at the color of this guy, well, obviously it's ash, so it's a little different. But what would it say? Would it say mafic or felsic? What type of composition do we have here? Exactly. It's light. Exactly. We can have the equivalent as, you know, these can be black as well if they're from mafic eruptions. Usually, I don't know if you know, like those nice barbecues outdoors, and they have the rocks, and they're not charcoal. They're actually these, but mafic.
Really?
Yeah. No, obsidian is what you guys were, the glass. They're just mafic vesicular rocks. So they're the same process. They cooled really fast and they were like fast flowing with, they trapped air bubbles. But because the magma was felsic, it was black. It was mafic, it was black. So that's usually what they put. It's not charcoal in the middle of those like ongoing gas fires. Fun fact. Okay, so yeah, once you guys finish, if you mind taking the pumice. So this is called pumice, by the way. It's hardened rocks from pyroclastic flows. Okay, very vesicular. It would float if you would put it in water. Okay. So that's one of the interactions, right? Ocean versus continent. Ocean would go down because it's mafic and it's denser. And you would get subduction zones with possibly some lava and volcanic eruption, which is why we get the ring of fire over the Pacific. Now, the second type of interaction you can have when convergent margins is if it was ocean and ocean, okay? Now, if you have two oceans colliding, what do you guys think happened? Or what do you guys remember happening? If you have two oceanic lithospheres colliding with each other, what happens? No, we're still in convergent, right? All of this is convergent boundaries. They come together, there's forces bring them together. Jawad, go.
This is wrong, but the older one, the under the younger.
Okay, what do you think that?
There's no-
Yeah, did anybody hear that? What Jawad said? Yeah, did anybody agree with that? Yeah, exactly. You guys are gonna do so well. I'm so happy. Okay, so exactly. When you have ocean and ocean coming together, the older one got more time to actually become denser. If you're in geoscience, you'll get to learn why. It's actually a lot more chemistry involved, and actually water comes in and things like that. But there are many reasons why oceanic crust would actually become denser as it gets older. Okay, so the older plate would go down and subduct. So you still get a subduction zone, right? Subduction zone is any time you have a plate going under another, and then the younger oceanic plate would stay at the top. Okay, the overriding plate is what we call it. Subducting plate is the one that goes down. Override. Okay, I think it's pretty intuitive. And same, we can have the same process as you mentioned, right? Sorry, what's your name? Tiffany. Okay, so you can have, again, the subducting plate can melt, magma can stay in the center. It can create what we call intrusive mafic rocks. Okay, intrusive mafic rocks tend to be what we call gabbro. Okay, so they're black, coarse, crystally rocks, or they can erupt. And if they erupt at the surface, they can create little islands, which are just islands of volcanoes that went emerged. Okay, and these rocks that cooled really fast, they're black. You can't see the crystals. They're mafic extrusive rocks, and they're called basalts. Okay. So that's our second type of interaction. Okay. And the last type of interaction is continent to continent. So what happens if I have two continents coming together? What's an example of two continents coming together?
Himalayas?
Exactly, the Kosh Mountains, right? So in the Himalayas, what happens? I mean, I think it's pretty intuitive, right? Yeah, orogeny, building of mountains, right? So if you have continents and continents coming together, you would actually have what we call an abduction. O-B, I'm gonna write it down. O-B-D, not abduction, not kidnapping, abduction. Okay, and abduction is basically orogenies, so building of orogens, building of mountains. Okay, and so this happens also between the African plate and the European plate. That's why we get the Alps. You know Zermatt, the Matterhorn? Yeah, that big. Have you guys ever eaten Toblerone? Okay, Toblerone, it's actually a real mountain on there. It's not a bear. No, you guys see a bear. It's actually a mountain too. That mountain is actually half African plate, half European plate. It's pretty cool. Eurasian plate is what we call it. Okay, anyways, abduction, convergent margin between two continents. Eurasian. That's Europe and Asian plate. African and Eurasian. Eurasian is one thing.
Yeah.
Okay, everybody got all of those three convergent margins? I know we went into tangents with the rocks, but we good? Okay, awesome. So again, subduction, abduction, got it all there? Awesome. Evidence for subduction zones, again, it could be ocean, could be ocean continent, is again what we talked about, the Binyak zones. Okay, so if you plotted all of those individual epicenters, because obviously if you have like a rock rubbing against another rock, that's going to create some friction, right? It's not going to happen continuously. It's going to be like locked in, so much pressure, and then all the energy is released. Okay, and during that energy release, an earthquake is initiated. Okay, P and S waves are emitted from that center, and once they reach the surface, they become surface waves. Okay, and we all feel it shaking. Okay, So that's the type of subduction zone. And if you plotted it, let's say if you had an ocean under a continent, okay? And if you plotted all the epicenters, they would fall exactly along the plate boundary. And that's what we call the Waradi-Binyah plane. This guy plus Waradi plane. Again, this wasn't, remember, if you remember, it was used as evidence for seafloor spreading, right? It can go about up to 700 kilometers of depth. And below that, it's too ductile, it's too soft, and there's no more enough friction, okay, for them to actually start becoming riptile or ripping. Now, I have a last rock I wanted you guys to show you. As you see, I'm passionate about rocks. I have like 50 rocks at home. There is what we call metamorphic rocks. Do you remember those? Let's cover this. 3 types of rocks: sedimentary, igneous, and metamorphic, right? So metamorphic rock, this is a rock that forms at depth, okay, by the partial melting of the rocks. So when I said that above 700 kilometers, the crust and the lithosphere becomes too soft to actually become brittle enough to create earthquakes, because you need very brittle, you know what I mean by brittle, by the way? Yeah, you need brittle fracturable plates to be able to create an earthquake. But at high temperatures, you can actually become malleable, and the minerals themselves, they can actually move. And that's where you form metamorphic plates. High pressure, high temperatures, that's when the crust becomes ductile, and you just change the minerals as they go because of such high pressures. Okay. So I realized we forgot to mention the 3 types of rocks, but now you have them. Okay, now divergent boundaries are where you have, you know, 2 forces acting against each other, 2 plates going away from each other. Okay. This happens in mid-ocean ridges. Okay, MORs. If you guys see this on the exam, you don't know what it is. Mid-ocean ridges. Okay. Now, divergent plate boundaries, okay, something has to push them away. We covered this, but just as a review, what's pushing them away? What's creating this divergent force? Don't be shy. Yes, okay. Exactly. Mantle convection, right? Hot magma coming up, it needs to go somewhere, so it's pushing everything that was already there to the sides. Okay, so the mantle, and we're going to go through this in the Wilson cycle, but this is basically, you can see how magma was going up, okay, and then new magma is replace old magma. Now this magma here is here, this guy, he's here, and now new magma pushes it away. Okay, we also call it ridge push. Okay, ridge push is the force that's actually pushing them away. Now these usually happen underground, so most of it would be, what's the composition of those rocks in oceans? Mafic. Yes, exactly. So these rocks would most likely be basalts because they're at the surface and they're mafic, extrusive. Okay. So this is how ocean floor is actually made. Okay. And these, a lot of details are part of the Wilson cycle. We'll get back to it. Right now, I just want to make sure we all know the different plate boundaries. Transform boundaries, again, the last type of boundaries we have, rubbing against each other. So none of them are actually going above or beyond, no mountain building, no orogenies happening. They're just rubbing next to each other. This is an example of California. So did you guys actually ever see the San Andreas movie with The Rock? Yeah? No? Love you guys say yes. Okay. So the big thing that every California is scared of is, oh my God, there's going to be an earthquake and one day we're going to get a tsunami. That's false. Okay. There might be a tsunami on California, but it's not because of an earthquake that happened in California. From what I told you, why do you think that? Okay. No, it's transformed. So the reason why what you need for a tsunami to form, okay, is actually a huge vertical displacement of water. That usually happens at subduction zones. If you have like a quick and rapid movement of that plate, all of the water that was here, do you see like between in that little wedge here, it's going to get moved up. That's huge, like over kilometers and thousands of kilometers. So that's usually where you would form the initial action for a tsunami. But we said that California was a transform boundary, okay? So there would never be a vertical motion, only lateral. So that means that if there was a big earthquake in California, sucks for them, they would die, probably, because there's a lot of reasons that are bad from earthquakes. But you would never have a tsunami form because of that earthquake, okay? Fun fact, so there's no vertical motion, only sideways. And that big thing that goes around South America, California, so separating the Pacific plate, North American plate, is what we call the San Andreas Fault, transform boundary. Okay. I also have a thing on divergent boundaries, okay, that I forgot to mention, really important. And we're approaching the end, guys, so bear with me. Okay, at mid-ocean ridges, we can imagine that it's like one plate, a second plate, and perfect diverging, okay? Let's see it, let's do it like this. So how many of you think that this is what a divergent boundary could look like? Yeah, you're wrong. Sorry. So actually, in reality, what happens is that when you have a curve, which naturally happens because it's a globe, right? There's actually going to be a divergent boundary. And then when there's these curvatures or there needs to form an S, they're actually just, their mid-ocean ridges shifts a little bit, okay? And it forms what we call a step-like transform boundary. So it would look like this, okay? Where is this? See how their plates are generally going away from each other, but instead of putting a perfect C curve, never happens, fractures in the oceanic plate make it that it just shifts if it needs to go. And in total, it kind of curves, but it's different fragmentations. Now, these, what's important, and you're gonna have a question, I know it, is that here, so highlighted are all your divergent boundaries, okay? This is where magma pushes up. But here, let's put a close up, okay? Let's go closer. See how this guy, this plate here, is moving this way because of this, you know, this step. And this guy is moving here. So what does this look like? Remind you of anything? Exactly. Not a transform boundary, but it's not between, well, it's not the major boundary, but it's a transform fault. Fault is any crack where there's movement across those two, okay? So between divergent boundaries, there's transform faults, okay? So if they say, oh, divergent boundaries exist, transform faults, that's true, okay? It's not only in transform boundaries do you find transform faults, okay? And that's because of these stepwise motion, okay? Any questions on this? No? All right. You following? Okay, awesome. Okay. Now, this is the last part. And you guys can go with questions and you can relax. Wilson, famous or fellow alumni from U of T, wanted to understand why we had oceans that died. Why did they form? Where did they come from? Because oceans are very dynamic, right? There are oceans that existed 1,000 or many million years ago, and now they're completely dried up and closed between two pockets. Okay, so the Wilson cycle basically is 9 different steps, or 1, 2, 3, 4, 5, 6 to 9 different steps that they describe how oceans form and close. So it's the life cycle of ocean. And the way he formed this is by bringing up all the concepts about plate boundaries, convection model, kind of brought everything together into a neat little life story. This is how the seafloor spreading works, okay? Looking at the protagonist is oceans, about that, okay? So we know that there's formations of supercontinents, the last supercontinent being Pangea, good job. And it was last together 250 million years ago. Okay, so what happens? You have a what we call a crypton, a peneplain. Peneplain just means that there's no mountains. Okay, you have a peneplain craton. Okay, that's your first step. So this is actually not, first step would be up here. Okay, It's why it's not a comprehensive, it's 9 steps because it doesn't include this. Okay, so your first step is that you actually have a peneplain craton, nothing. Okay, this is your Pangea supercontinent. All the continents are together, or continents in general together. There's no origins, there's no mountains, generally not fractured, pretty flat. Okay, like here, Toronto. So old, one of the oldest places in the world, actually. Anyway, then what happens? You actually have magma. Let's say it couldn't stay near the core, so it started to rise up through convection. And it randomly comes up, and it happens to come up below a peneplain craton. What happens? Well, there isn't like a divergent boundary formed yet. So the craton just, the plume, the mantle plume, which is what's coming up, right? I'm gonna call this plume. It doesn't have anywhere to go yet. So what happens is that it accumulates and it kind of creates a bulge within the craton. And we all know that rocks are brittle, right? So when it forms bulges, it's going to start forming fractures. Okay. And along those fractures, there's going to be movements that's going to be faulty. Okay. So you have, going back, first, nothing happens. 2, a mantle plume creates a little bulge and starts to fracture, not yet completely fractured, but starts to fracture the craton. Then what happens? You actually have, again, this is not, I can't stress this enough. Okay, this is, let's say, put 2 and 3 together, because what happens is that you have the bulge and then it starts fracturing, and what you have is rifts. You start having faults. Okay, there's no oceanic floor yet. All of it is felsic or craton material. None of it has been lava yet. Nothing has erupted, but you start seeing faults because of that bulging. And that's the rifting stage. Okay, early rifting stage. Okay, once it rifted enough, naturally it starts erupting. Okay, and all of that magma plume, it finally reached a little bit of surface. It became lava, and it's creating new oceanic plate finally. And that's what we call a juvenile ocean. Okay, there's a little bit of water that can be accumulated through rain, through the connection to other seas, through other methods, but you just start seeing ocean floor. That's your biggest indicator. Before there was rifting, but there wasn't ocean floor. Example of this would be the Red Sea. Okay, that would be an example of you start seeing a little bit of ocean floor, but not enough to consider it a full ocean. You call it a juvenile ocean. If we came back to Earth 100 or 200, 100 million years ago, from now, this would probably be the size of the Pacific. Okay, it's pretty insane. It wouldn't look the same. Okay, once it becomes a mature ocean, it is what we see in the Atlantic now. Okay, it becomes so there's continued here, there's divergence. Okay, it's not shown in the picture, but you have the Atlantic, so you have your ocean creation, and then here you have passive margins. Important word, note it down. Okay, you don't have a subduction zones, you just have ocean pushing continents away. Again, now we have our explanation of how continents move. Okay, it's the ocean plates pushing, or ocean pushing continents away. Okay, so no subduction, you just have growing mature ocean, and that's the current Atlantic. 6, now it's about 150, 200 million years since it formed. Crust is getting really old, getting dense. So what happens? It actually starts breaking off. Okay, the ocean and continent, the continent's still proud and still floating, but the oceanic crust starts being too old, and it's like, you know what, pal, I give up, I start subducting. Now you have subduction zones, what we call active margin. Why? You would probably see, well, it's moving between each other, and you probably see volcanoes, earthquakes, things like that, tectonically active. And these are the first sign that an ocean is dying, because now it can't just grow anymore, because the more it pushes, the more just oceans kind of go down. Okay, it doesn't drive any external force anymore. Okay. Then what happens is that probably in the middle of, while you were mature, you formed little islands, or you form different things like that. And now these islands, while the subduction continues, they actually bump into each other and they form big cratons. So they start, they converge, they collide with each other, and they suture. Okay, they suture on each other. Okay, so continents with continents kind of stack up. Okay, and then finally, what happens is that there's no more ocean, and what you have is continents from this side of the ocean previously. So which would be maybe in a couple of years and a couple thousand million years. Europe with America. Okay, right now it's mature, it's gonna be dying one day. So both continents finally come together. This is the end of the ocean's life cycle, and you have abduction. Right? Origin process and the closing of the ocean. And that's it. And then erosion happens and you're back to your first kind of thing. Okay. An example of the convergence is abduction. Abduction is in Himalayan mountains or the Kolsh mountains, right? And what's interesting is that there's proof of this. If you went and hiked up, 5,000, or if you hiked up in the middle of the Himalayas, what was really interesting for scientists is that they actually found mafic rocks. At first, they were like, why do I see mafic rocks when I'm on top of the Himalayas? The reasons are, it's actually some of the remnants of the dying ocean. Okay, it didn't get subducted at the last minute, it just stayed at the top. Which one? Before mature. So it went juvenile to mature. Oh, the 3 is because in this diagram, 2 and 3 were together. So 2 is rifting, 2 is bulging, 3 is rifting. Okay. So when you have bulging, you don't have these rifts yet. Okay. So this technically this is 3. Okay. And it takes about 300 to 500 million years to actually go through the entire cycle. Sorry, at the back, go for it.
Really dumb question.
No, there's no dumb questions.
So on step 1, there was an ocean above that surface.
No, this is just a supercontinent.
Where did the between those two, between step 1 and
Oh, I see. Okay, well, even when you have supercontinents, it's not like the entire Earth is covered by continent. It's just one packet of continent, and everything else is just a single ocean. So if you start cracking it and enough of it spread, some of that ocean can like come in. See what I mean? It's like if you have an empty valley and it just, new space to fill in the water. And usually in the early stages, what's the sea? The sea where a lot of people are like, this is the saltiest sea that exists. Exactly. The Dead Sea, the reason why is that it's such an early juvenile ocean that's all rainwater and salt. That's all it is. And a lot of seas start off like that. They didn't connect with other oceans or other seas yet. So it's just the product of, as I said, the water just comes from precipitation. And then it gets to connect with oceans. Okay. Answer your question. Good question though, honestly, because I didn't mention that. Any questions? Okay. All right. We can go straight to the questions. I think it's good that we go fast for this one. And I think, oh shoot, no. So path of margin, think of the east coast of North America. We don't get a lot of earthquakes, no subduction zone. Okay, it's just ocean pushing continental crust. Active margins, you get subduction. Okay, so you get a lot of volcanism, volcanic eruptions, earthquakes, because there's actually, one plate going under the other. So ocean going under continent.
when you say the ocean pushing the continent, like actually the weight of the ocean pushes continent, or how does that work?
No, so it's seafloor spreading, right? So it's continental crust or continental oceanic lithosphere that's pushing what was originally two connected continents, right?
Right, so from the, okay.
Yeah, exactly. So it's like you create material that's pushing it away.
And for active, is it only subduction or is it like transform?
No, so active margins is between continent and oceans. Okay, and so no, generally it is it's only if you have a boundary between ocean and continent, it's going to be.
Is it like the west coast of North America?
Yeah. So again, when I mentioned the west coast of North America, I want to really be particular about this because you guys are going to get confused. Okay, where is my map of California? Okay, see how here these are like different legends that we use in geoscience. Here is a transform plate. This is not an active margin here, okay? All of this place here, when I said West America, I meant kind of like Western Canada mostly, okay? Because Western US, this is all, it's not active because it's not a subduction zone. It only becomes a subduction zone in Northern Canada. Okay, that's where subduction is. Those triangles means that it's the direction of subduction. And there's no triangles between transform boundaries. Okay, so what I mean when Western North America is specifically this area, that's active. And then if you looked at the world of the map, this active boundary would go all the way to Alaska and the Pacific Rim of Fire, all subduction. But here it's not, making sure. If there's no subduction in San Andreas. Any more questions? No? Okay, now we have questions for you. So
Oh, there's only like 20 or so. So,
okay, there's only 20 questions. The issue is I have all of the answers in PDF. So they're all.
Oh.
You can see them. It was supposed to be an animation. Shoot. Let's do this. How are we gonna do this? How are we gonna do this? Let's see.
You all have slides, right?
yeah.
Oh, thank you, Krish. Okay, well, I guess you guys all know the answers.
Yeah.
Is there even point asking them? Okay, you know what? How about we do a speed go through, make sure everybody understands the answer.
Yep.
And then we see.
Okay.
Let's just, because the professor actually emailed us, I want to make announcements about what she said first. Okay.
Okay. Oh, I also did add some like questions at like the last minute. So I
Oh,
don't know if she
okay.
saw those.
I don't have them either because I have a PDF.
Oh, okay. Well, I
So-
have.
Okay, do you mind resending them through email maybe?
Uh,
PDF email.
Okay, sure.
Okay. Here, or I don't know if you can see this. Okay, I hope I can hide. Okay. Okay. So
Yeah,
this is from the
I don't know
professor.
if these changed because I also.
That's okay. Alright, so ignore the questions because you might have changed this.
Yeah.
Okay, she's not likely to ask about the exact dates when you're looking at the plate tectonic paradigm, okay? It's mostly just the era. So kind of what we were talking about getting a general sense of how people came up with the plate tectonics, okay? Went from Atlas to actually becoming, becoming more of the plate tectonic continental drift, and then finally seafloor spreading. Okay. So you wouldn't try to trick them by saying a date that is a few years wrong. Okay, it doesn't matter. Don't worry about that. You didn't cover on Benioff zones in the lecture this year. It mentioned module, that wasn't a big thing. I don't think it's on the exam. Okay. Something less to study, but at least you know about it. Might as well. Extra proof of subduction, right? The number of plates is not precise. It depends on how you count them. Oh yes, that was one of our questions. We said how many plates, there was debate, is there 24, 27? It doesn't matter.
I think.
I think
question-
you were the ones that brought that up last year, actually.
Yeah, so some of the questions got cut. A lot of the questions got cut actually.
Okay, the exact numbers of mass and volume, different layers wasn't a huge theme, so don't worry when I said 2/3 of the mass, 1/3 of the mass, and just know that it's specific. Also just be a bit careful with the Wilson cycle. Yes, so the stages are different. We covered this right together. The table didn't cover all of the stages, so I can go back to that slide. Okay, so it's not important to exactly know, but yeah, what happens, you need to know what happened, but as I said, some of it was messing, which was mostly the fact that there was the peneplanes and then the rifting that happened. Okay, and then passive active margin. I think that's it. I'm not supposed to be sharing this with you guys. So,
Oh, okay. Well, I guess there's not really any point. So I also said in the Zoom call, yeah, just I guess since we given the way this was run, feel free to look at the questions on your own and reach it, or we could go over them very quickly.
You
Yeah.
wanna ask them what you wanna do?
Yeah, what would you guys rather do? Would you guys, I guess for people on Zoom, you guys can just leave a thumbs up for which answer choice or for what you would rather do. So we could either just speed run all the questions, just make sure everyone understands, them, or we can just,
Or we can go through the questions really quickly.
Yeah.
If anybody has any questions, we'll cover them and we'll
Yeah.
explain the solutions. What should we
Uh,
do? Do the questions? Okay. All right. Question 1. Which of the following states is incorrect? Okay, so let's check which ones are correct and see that we actually know this information. Okay. 1. P waves. So remember Slingy or whatever that guy. P waves are first waves recording in the seismograph or station if you're a geologist. Yes, because they're the fastest one. Okay, correct. Let's go to C. S waves stand for secondary waves. Yes, also easy to remember. They're the second ones to come, right? S waves, secondary waves, and P waves are primary waves. Yes, true. Also, great memo, PF. D, S waves are transverse waves, while P waves are compressional waves. Yes, we talked about this, right? The spring, compression, extension, and then S is transverse. I didn't cover exactly the term, but it just means wicking around. Okay. Now, which one is incorrect? B. Secondary waves travel through liquid and solid. The P waves travel through solid only. So it's the other way around. Okay. All right. Question 1. Questions? Question 2. Oceanic crust is much more dense and silica rich than continental crust. That is true. Now there's 2 statements to verify in a true or false question, right? Even if there's one word that's wrong, that makes the whole statement wrong. Make sure. So oceanic crust, okay, more dense. Yes, we know that. That's why it goes down. That's good. Silica rich, we know it's mafic, okay, dark, and okay, no. No. Okay,
I'm sorry.
it's wrong.
I'm
think we
sorry,
covered it in
I
the-
think, yeah, I might have also moved.
It's okay.
Okay, yeah,
Okay.
let me.
No. Okay, so felsic, please ignore that. Oceanic crust is denser, but it's not more silica rich. It's silica rich. Okay, this is good. At least we went over it. Okay, if your first statement is correct, doesn't mean that your second word is correct. Make sure both are correct for it to be a true answer. Okay, because reading up really quickly, Pascal's a good student, but he probably saw the first term and was like, yeah, that's right. The third, that's not right. Okay, mafic, think about it as Hawaiian, easy flowing. Okay, Hawaiian is like mafic. I don't know if you guys knew that. It's mafic rocks, and it's easy flowing, and it's very, so it doesn't have a lot of silica or plastic to stop it from flowing. Felsic is explosive. It tends to be silica rich. Felsic, maybe you can use it stick. Felsic, I don't know. But it's not, it's silica low. Question 3, which of the following geologic features can we expect to see near subduction zones? All right, let's go through all of them. So liquefaction, what is liquefaction?
There's like an unstable base, so like when there's like an earthquake or something, it like could not this a little bit.
Yeah, exactly. So when you have, yeah, exactly. So when you have, I'll just elaborate a little bit more. When you have quick clays, okay, which are clays that are kind of saturated in water, if you shake them, right? You shake them, what happens is that all the clays kind of collapse together, and all the water that was previously just kind of within the clays in general go to the surface, so it creates a very liquid surface. Okay, that's usually when you see houses that can sink up to like 5 meters down. That's because of liquefaction. Quick clays. Now, enigmite deposits are the results from pyroclastic flows. Okay, so yes, we know that at subduction zones, it can be volcanoes. Volcanoes can actually lead to pyroclastic flows. So it would lead to enigmite deposits. And then we covered this by covering the San Andreas myth, right? You need a subduction, you need a vertical displacement of water to create a tsunami. So yeah, you can have a tsunami wave created by subduction, right? Because again, let's see stage 1, just in case you guys, you have the subducting plate and you have the overriding plate. This is water here, okay? So you have all this volume, and the second scenario, you would have this plate move, okay? And so all of this pre-existing wedge here, with the water here, all of this water had to be moved here. Do you see it? Yeah, it's like you're pushing water all at once. So that can create tsunami waves. Okay.
Does liquefaction always happen at subduction zones?
No, because it depends on if you had quick clays to begin with. If it's all granite, all of your things is just solid rock, then you don't have all of those sediments to actually give off water.
So for these kind of questions, I feel like I would get tripped up because they say we expect, so I would assume it means all the time.
I think from this question, it's more like, what can happen?
Okay, like possibility. Okay.
Yeah. Good question though. Also, earthquakes can also occur on transform boundaries, okay? So liquefaction would have been a good valuable thing for transform as well. Question 4, which of the following plate tectonics is incorrect or impossible? Ocean transform boundary. Yeah, sure, why not? Right? There's nothing saying it can't happen. Things are coming. Okay. Ocean, let's go to C. Ocean continent subduction zones. Yeah, can happen. Okay. Continent
I don't,
kidnapping zones.
yeah, we
Oh,
will,
that's
we will fix this.
Okay.
I will make,
Continent abduction zones. Yes, Himalayas, Cliff Mountain. Now, what about this one? Continent subduction zone. No, never happened. Continent can never be like underwritten because it's too, it's dense. It wants to float. It can never go under, no matter how old it is. Okay. That's just because generally all of the continents have the same age. Okay. Now, which of the following are modern examples of a closing or dying ocean? Again, this is wrong. This is the right answer. Okay, update that on your slide. That's what the professor was referring to.
Yep.
Okay, the Pacific Ocean is a good example. Why is that? Why do you think it's a dying ocean? What are some of the evidence we can use? Using our geology toolkit. Oswald? What do you know?
hotspot. I think she
Oh,
said.
hotspot tracking. Oh, that's good for, sorry, I was like, do you know something that I don't? No, it's hotspot tracking is a good evidence for, so Hawaii is a hotspot, right? So that's not a divergent plate or anything. It's just an evidence to show plate movement. But it could be a mature ocean, right? It doesn't have to be dying. It could be any plate moving. But it shows that it's moving. What should we show is subduction zones, right? If you have a subduction zone, that means you're in your dying phase, so it's not pushing anymore. Active margins. Okay. Atlantic Ocean doesn't have any. We don't have any subduction zones around the Atlantic, so it's not dying. Red Sea, we said, is a juvenile ocean, and of course, it's not all of them. Any questions about this? Question 6, the East African rift is an example of a convergent plate margin. No, it's not. It's an example of one of the first few phases of the Wilson cycle, right? It's not yet an embryonic ocean, but it's just a rift phase, okay? It's right before ocean forming. So false here.
Yeah.
Benioff zones, okay, again, you don't really need to know this, but might as well. Are evidence for what? And we said it was earthquakes along that subduction plate. Polar wandering. Yeah. What could be evidence of polar wandering, so it's not right, is that remember what we saw about the magnetic stripes about Harold seafloor spreading? That could be an evidence, right? Because the poles move. That's why you get north, south, north, south. Earthquakes. Tricky question. No. Yes, but at least 2 could have been yeses, honestly, could have been 8s. But again, doesn't matter. Question 8. Which of the following was not a piece of evidence used by Wegener in the support of continental drift? Okay. Remember, when we have to think about Wegener, we have to think about fossils, ice, plants. And we also have to think about how he formed this in 1915. When did we say that the seafloor stripes were discovered? In the late 1940s, actually. No, 1960s. They were actually discovered in the 1960s. It was actually pretty cool the way they figured them out. It was during the Cold War between the America and Russia, or USSR. And what happened is that while they were using, they wanted to detect Russian submarines. And the way they did that was using MADS. And so basically, a lot of the geology findings that we find are actually from the military. A lot of it is like a lot of environmental science comes from the military, sadly, but it's true. And so while they were trying to detect different ocean submarines, they were recording magnetic, right? Because ocean submarines are made of metal. So they would disturb any magnetic pulses. When they did that in the ocean, they realized, wait, why are we seeing maps of white and red and like positive and negative? Makes no sense. Like, is this Russian Morse code or something? No, it was actually, the bottom of the ocean floor. And that was evidence for seafloor spreading. So was Wegener able to discover that? No, he was born in he formed his thing in 1915. Paleomagnetism stripes were discovered in the Cold War. Okay. He also didn't have the technology to discover that. The discovery of cold mires and glacial deposits. Yes, we said ice. Match of rocks in now separate continents. Yes. And the shape of African and South American coastlines. Yes, we could have also added fossils, okay, and plants, which describe the different climates. Or climates could also have been described by the type of rocks, okay? Okay, what is the relationship between continental drift and plate tectonics? Okay, plate tectonics is a theory that explains the observation of continental drift, right? We've been wondering this for a very long time, basically since the 19th century, when mobilism took over, right? Continental drift, the official word was Wegener in 1915, but people were suspecting, right, mobilism for a while, since 1958, doesn't matter. But so yeah, plate tectonics actually provides convection and a mechanism for doing it. They're not the same thing, okay? Because without continental drift, without plate tectonics, continental drift would to this day still be rejected. But there are two separate equally valid hypotheses. Note they work together. Continental drift is driving mechanism for plate tectonics. No, it's kind of the opposite, to be honest. Any questions? Interrupt me if I question 10. Many features in the Earth's seafloor physiography were not elucidated until the advent of sonar. Did she say anything for question 10? No. True. Okay. As we said, a lot of new technologies, it's very recent science. You need a lot of those technologies in geophysics to be able to actually determine these things. Where is the majority of oceanic crust created? This is wrong.
Oh,
You guys all know by now that the answer is, where would we have oceanic crust created? Exactly. Thank you.
yeah, okay, I don't know why, again.
Bravo there. Okay, not all of the above, not all the above. Transform, nothing's created, nothing's destroyed. Okay. And conversion, you'd actually have things by or by.
And also the mid-ocean ridges.
Yes, divergent boundaries include mid-ocean ridges, right? They're basically just mid-ocean ridges. Yeah. Yes, divergent boundaries also include rift valleys, which are not mid-ocean ridges, right?
All the rift valley in Africa.
It's a divergent boundary, because divergent just means you have divergent forces against two plates. Does that make sense?
But in Africa, then it's like two continent plates are divergent.
Yes. It's just, you have to look at the general sense of the forces that would tell us. Divergent, convergent, that's one.
Something with ocean ridges, is it diverging, like oceanic, like?
Ocean.
Okay.
Yeah. Because the ocean's being built and it goes on the sides. Symmetric.
So this is continent, is it continental oceanic, is that a thing?
No.
Oh.
Oh, she's a question.
Oh, yeah. That's a good question. It actually, the plate, remember, is crust plus lithosphere. Okay, so it just gets embedded within the lithosphere because you're creating crust, which is getting on top of lithosphere. Make sense? Any question? It's a good question, actually. I want to respond further, but I don't want to you just spawn a whole thing. Okay, question 12. Which of the following describes continental crust just beginning to split apart? So just beginning, remember one of the first stages, it didn't have water, so you can remove all the ocean names, okay? And it was just the Rift Valley, Africa, right? Questions? Nope. Question 13, seafloor spreading implies the seafloor, that seafloor rock should be the same age, younger as water becomes colder, or youngest and on the crust of mid-ocean ridges, shouldn't be on, it should be like near mid-ocean ridges, and or youngest on continental shelves. Continental shelves are along passive margins, Okay, so not subduction, it's just the accumulation of sediments across passive margins. So what would you say is, well, C, no, so youngest, because that's where all the new ocean is being embedded within the new lithosphere. Yeah. Questions? Yeah. You can ace this, to be honest. The largest zone of Earth's interior by volume is the mantle. Now you know, you don't care, but. Question 15, the sliding of the sea floor beneath a continent is called subduction. Okay, again, they are sliding, but that's not subduction. I think we've covered this by now. Question 16, most of the oceanic crust is made up of basalt, mafic, and also extra fine grain. Just remember that. If you want to go into all these details, the granite could be. Yes, exactly. Great writing going on. Dewan knows. I'm just gonna say great handwriting. You probably know it. Peridotite would be. We'll cover this in the midterm review session, but
Organic?
no. Peridotite, if I give you an index, it's usually olivine and green.
Who's the mantle?
Exactly. Ultramafic and mantle. Now, limestone, usually found as continental shells. It doesn't form through magma, okay? But it's actually a sedimentary rock, okay? And it's formed from CaCO3, okay? It can form different ways. You don't need to know this now. If you want to know it, ESB20 is a great class. Okay. So yeah, the only valid one was basalt. Question 17. The Afar triangle. Oh, did you have a question? Peridotite?
Yeah.
Oh, that says mantle.
Yes,
Yeah,
this
they
is,
did a lecture about my ways of saying M. It's valid in France. Okay. Yeah, I didn't know. No, that's it. There we go. There we go. Okay. Question
oh yeah, this is
17.
the,
The
yeah.
Afar triangle isn't.
this is a homage to a previous exam question that just stuck with me.
Oh, it was actually in the exam.
Yep.
Oh, great question. The Afar triangle is a musical instrument. Do you want to say?
Well, yeah, so firstly, this is a sort of a reference, a little bit of a homage as well to a previous exam question. Anyways, yeah, so the Afar triangle is a musical instrument played by geoscientists and non-geoscientists alike. Very difficult question.
Yes. The Afar triangle, actually, does anybody know what it is?
Yeah, does anyone know what it is? What it actually
I
is?
see none. Oh, go for it. Or who? You guys like compliment each other, so go for it.
Yep. Mhm.
Yeah, exactly. Were you gonna say that?
Yep.
Okay, so, yeah, I'm gonna add on to, people don't know what the triple junction or Mercedes, I like to think about the Mercedes logo every time I think about it. So it's like when we thought we looked at it as a 2D mechanism, but it actually happens in 3D, right? So when you have a mantle plume come in, it doesn't just like break the crust one plane, right? What actually forms is that, let's say you have your mantle plume coming up here, and what happens is that you would actually have the crust break or the craton break 3 ways, okay? And then rifting would happen, and eventually one would give in, okay? One of those arms would become what we call an olacogen, okay? And they would stop growing and becoming a rift, and then the 2 others would become an ocean. But then you'd have this one arm of the Mercedes, or the triple junction, that just, it started to break because that's how the physics of it had to work in 3D, but then the general motion only worked along 2 arms. And that's why it's curved as well, right? There's no one perfect, it's because it always had like a 120 angle to start with. Okay, and then it became an ocean. Olacogen, I love to put fun facts, also we're reaching the end. We actually are near an olacogen, okay? When the Atlantic plate originally, or the Atlantic Ocean originally formed, it had like this Mercedes, right? This was the Olacogen, okay, let's say. Okay, and this is, let's say, North America, okay, and this is Europe. And what happened is that this continued to form divergent boundary and form the Atlantic, but this guy, the Olacogen, never continued to open. But we're on it. And there are actually some studies now that are saying the Olacogen might, there's some like evidence of reactivation. So right now we might actually be seeing the Mississippi is the Olacogen, okay? All the Mississippi Valley, the reason why it's such a valley is because of the Olacogen. And there's some people saying that maybe one day it might start getting reactive. There were evidence on that in glacial deposits. And so this might become actually an ocean, who knows? Or a juvenile rift basin, which is concerning considering it's above the Pickering nuclear waste station. But fun facts, you might die. Chernobyl number 2. Don't worry, it's not now, but there are some people saying that.
Oh, yes. So these are my questions. Yes. Features. Yes.
My ideal world. Where tectonic plates move at a rate of 30 meters a minute. Last year, she moved to a house seemingly in the middle of
Oh,
nowhere.
yeah. I think all the math is wrong. It should be like, I think it's a day. Sorry.
That's okay.
The math is wrong.
Today, she noticed that 2 plates
Yeah.
that she lived in are about 100 kilometers closer to each other than when she first moved into her house. There's also now a wedge of lithosphere protruding out of her floor. This suggests that Charlotte lives in a, that's a cool question, actually.
Yeah.
Okay,
I don't know. So I have like 5 or 6 of these like types of questions.
let's go. So what are some of the advice that you could probably see? Let's look at some of the evidence, okay, that we have to look for. So today she notices that 2 plates she lives in are closer to each other, okay? So the plates, that is already an evidence of what type of margin. Probably. Exactly. They come closer. This is a really nice one, actually. Thank you, Pascal. Okay, we know it's convergent. Then there's also a wedge of lithosphere protruding out of her floor. Okay, so what would that tell us? That, yeah, because it's orogeny, right? Maybe a little bit of mountain building going on. So this could probably say it's orogeny. So abduction, exactly. Okay, so if we put convergent, we know there's 3 types. And if it's an orogeny or abduction, we know it has to be continent. Okay. Question 19, Pascal lived in the same parallel universe as Charlotte, so 30 meters a day. Last year, she moved in a house on an island. He moved on a house on the island. So that's already an advice, right? We all know probably it's going to be something we know about. There's a volcano on the island. Okay, volcano island sounds awful like a volcanic arc, right? Volcanic. So already looking for volcanic arc, we would probably know that it's one in the ocean, and there has to be protruding mantle, right? Not on an arc, but a protruding island. Today, he notices that the volcano has become inactive. Okay, another island just out of the view seems to be created where the island he lives on once was the volcano coming out. The island Pascal lived a year ago, was the top of it. So basically what he's saying is that you had a little mountain, it was a volcano, and then it stopped being active, and instead this moved and another volcano is being active. So that's hotspot tracks, right? Hawaii. Okay, so this is suggesting that you have a moving plate over a non-moving mantle plume. Okay, so hotspot. I think
Yeah. So
we might
there's
not have enough time. Rihanna lives, okay, let's see. Euro, spot on island. The
Right.
islands were right up against the coast. Okay, so we're moving towards something convergent, slightly sinking, probably liquefaction, and earthquakes, so subduction zones. Professor Kennedy lives in the same episode parallel. She moved to a house in the middle of the ocean. Today, she noticed that her ocean seems bigger. Okay, probably a growing ocean. So it could be juvenile or mature, right? Because both of them are growing.
So ocean always growing?
No, because it could be dying.
What's that growing?
Pacific dying ocean.
Right.
A dying ocean
So how do we know that?
because of subduction zones, remember? Once the margins become active or they become subduction, then there's
Oh,
no
yeah,
more
the
pushing away.
perspective is heavier swing down. And then-
Yes, exactly. Exactly. Last question, Professor Isles, we miss him dearly. Moved to a house in the middle of the ocean. Today he notices that the ocean's being smaller, so dying ocean. There you go. All right, and we just made it. Thank you
Yes,
guys for bearing with us for 2 hours.
yes.
I hope this helps. Okay, feel free to also go
Yeah,
back to the
so-
QR code.
Yeah, so I guess there's a few things. So firstly, everyone on Zoom, if you did not fill out the attendance form, it is on the first slide for this review. So please fill that out. Really helps us. Yep. Additionally, you guys can see the contact our contact info. It's like closer. Okay, so the people in person cannot, but yep, Zoom people, I'm on that slide right now. Additionally, I would like to promote 2 Discord servers. So one is in just a general like UTSC environmental science server. We have an EESA06 channel with Charlotte and Rihanna and we are all a part of. Additionally, we're all in the EPSA Discord server. So 2 QR codes for those respective servers. And yeah, honestly, thanks for coming. Best of luck on the midterm I believe it's in 2 days. So yeah, just feel free to reach out to us. Any last minute burning questions you might have, of course, reach out to your prof as well. And yeah,
Like, does open booking open internet license?
I took it in person. And I'm not a TA for this course, so I can't.
Yeah.
But yeah, what was your experience?
I mean, for me, I just really, it is open note, yeah. So pretty much just have my module notes open. If anyone took them, if not, you guys can just, what I did is I just saved it as a PDF and then I just copy and paste all the text. And then you could use that, to obviously control find or command find. Yeah, I don't know if you have some time, read the textbook. I don't know who does. Yeah, so I don't know if it is open note or not, but yeah, yeah.
As much as I hate to say it, it is a bird course. I know most of you are not gonna do geology later on, but if
Yeah.
you do have any questions about geoscience,
Yeah.
don't, you can contact me or Pascal. but-
Yeah, we will. We
Hopefully
also
it
need to make some
makes sense.
edits to the questions that you saw.
Alright,
Yeah, I guess I'll
did you-
change around. I'll make sure everything is pointing to the right
Oh,
things and
it's
then
much
I'll
better,
send it
right?
over.
It's
Yeah,
Much like,
no worries.
for my
Oh,
opinion,
yes,
I think ESA pen is science enough. So this goes more into rocks and all of the science. stuff. Alright, thanks, guys. Thank you for coming. Good luck.
All right, yeah, thank you everyone for coming. I guess session adjourned. So yeah,
So, is there a specific reason why the continental lessons are mostly basic rocks?
Yes, so actually, it's a lot of what we do in